because I've been a bit of an intermittent attender of the seminars, but I think I've seen most people around. For anyone who doesn't know me, hi, I'm David. I did Bachelor of Science in Arts dual degree and then BSc with honors, UQ. I just finished up in June this year. And I apologize if it's I don't really know how well my connection is here. I'm currently calling in from Lake Tekapo in New Zealand. After I finished honors, I thought it would be a great idea to come over to New Zealand for a 1 month backpacking trip. And I'm still here because my flights back were canceled because of COVID. And I've just decided to stay here because I have no compelling reason to rush back. So can everyone see fine? I don't know. I don't know if I should go full screen or I don't really know how this is looking on your screens.
Yeah, go full screen.
Yeah.
This exact same problem before. Is that better? I know there's like a F shortcut to go full screen. You know, that's fine, isn't it? Cool. Right. There's a couple of people nodding, so I'm going to assume that's cool. All right. Yes, I'm David. I did my honors in this, and it was a lot of fun. So my interest is generally in the field of computational topology and geometry. I didn't really know anything about it before honors, so it's still, I'd say, relatively new to me because it's just a convergent point of so many different fields in mathematics. And even after a year of honors, there's still so many things I haven't really, even in my thesis and presentation, I didn't delve a lot into. So a lot of things in homology theory and combinatorics of triangulations of three manifolds and polytope theory and all this sort of fun stuff, which is what I'm sort of doing a lot of study on now. For the past month, I've been waist deep in Ziegler's lectures on polytope theory, which has been good fun. And I also like to continue studying this sort of stuff in the future when I do a master's or PhD eventually. Other than that, I'm pretty interested in ancient history and Assyriology, so like ancient cuneiform mathematics and computational linguistics. There's just a couple of other side interests that I enjoy doing stuff on in my spare time. So today I'll be talking about computing the Thurston norm, an approach by normal surface theory. Now, sorry if you can still see the whole thing, right? I've just got like another tab up just on the side of my computer where I've just got a couple of notes that I haven't got in the presentation. You can't see that, right? It's just the presentation. Awesome. So I'll delve into it. So I'll quickly just look through, this is basically more or less an slightly adapted version of my honors presentation. So apologies to Alex and James, who probably already seen it before, or most of it before. So just go over the quick motivation and background of the Thurston norm, an overview of the norm itself and its unit ball. We'll delve a little bit, I'll give a brief overview of normal surface theory and why is it worth considering an approach to the Thurston norm by normal surface theory, and then just give a brief outline and example implementation of an algorithm that takes a three manifold and gives you the Thurston norm unit ball. So I'm pretty sure everyone who's ever done, I'm pretty sure almost everyone here has done discrete mathematics and probably knows, some degree of low dimensional topology, but I'll quickly brush over anyway. So a triangulation on the three manifold is essentially just a discretized version of a discrete structure that you impose on three manifolds. So you take a certain number of n tetrahedra and you glue them together in a way that represents or really is that three manifold. So as you can see here, so you just take certain tetrahedra and then glue it together and you can form the torus or whatever. So pretty much almost every algorithm in computational topology will use this discretized structure of three manifolds, or these triangulations, as an input into the triangulation. And most of them will test for various topological properties by enumerating embedded surfaces within that triangulation. So, for example, unknot recognition, you'll import a triangulation of a three manifold that represents the knot complements. And it's been a very, very successful field so far, but the computational efficiency and algorithmic efficiency remains a very key issue in many of these algorithms. So in particular, the main problem the Thurston norm tackles and that other measures of topological complexity aims to tackle is this problem of algorithmic complexity, that it increases exponentially with the number of tetrahedra in a three-manifold triangulation. So I'll delve into this a bit later, but consider z to the 14n. So where n is the number of tetrahedra, the more you increase, of course, that number is going to go up exponentially. And if you consider z to the 14n is the, again, I'll go into this later, but it's like the dimension that we're sort of doing computational stuff through, the higher n is going to be, the longer it's going to take. So as a quick example, I suppose, this algorithm that I'll look at later, I ran it on a, you can run it on triangulation of like 2, 3, 4, 5, 6 tetrahedra, and it takes a couple of seconds. I think I ran it on like a 10 tetrahedra triangulation and took a couple of hours. Oh, sorry, 10 tetrahedra triangulation took a couple of hours. And I think I tested it on a 14 tetrahedra triangulation and it took a few days. So that was good fun. I think Ben Burton, my supervisor, mentioned he ran it on a 15 or 16 tetrahedral triangulation and took a couple of months on UQ's computing cluster. So you can see the key issue here is that you get to 13, 14, 15, pretty much anything above maybe 11 or 12, you're going to be talking about days or weeks or even months. So we want to keep the number of tetrahedra at a minimum, which is one particular measure of sort of topological complexity, is a number of tetrahedra it takes to build a triangulation of a three manifold, but we also want to minimize the exponential base in such a way that it solves the problem of reducing the running time and the computational complexity, but without losing any important topological information. So, as an example, triangulation of a torus, you would not want to enumerate surfaces in that. So here is where the Thurston norm comes in. Essentially, the Thurston norm is the central concept of three-manifold topology. Provides a fundamental measure of topological complexity on embedded surfaces within manifolds. So computing the Thurston norm obtains the minimum genus of these embedded surfaces, which provides information about the complexity of the manifold itself. It was originally introduced, of course, by William Thurston in 1987, I believe, in the paper that appeared in the American Mathematical Society with David Gabai's paper on something else. It's quite famous, I just can't remember right now. And it was originally introduced in its applications to fibrations and foliations of three manifolds, but is now, of course, much more widely recognized as a very important tool in its ongoing contributions. So, so essentially what we want to, it is defined for a certain class of three manifolds with a non-trivial second homology H2 on some manifold M. And as I mentioned before, it measures the complexity of surfaces representing a class of the second homology for certain three manifolds. So we'll sort of, there's a few steps in between, and it's sort of where normal surfaces come in. I'll get into it later, but essentially we have some sort of manifold and we want to do topological analysis on it by looking at embedded surfaces. For those surfaces representing a class of the second homology, we can calculate the Thurston norm of, which will give us essentially a rough generalization of the knot genus. So we can sort of see a very brief expression here that's not super important in this talk. So the Thurston norm of some homology class phi, which is represented of a surface, is the minimum of the sum of connected components, a minimum number of the sum of connected components where that satisfy a negative Euler characteristic of some surface S. So it's defined on a map, which maps from the second homology of a manifold to the reals. So this is Thurston's original definition, not accounting for the discretise structure of normal surfaces. Klein minus measures like I said, the rough generalization of a knot genus, excluding torus, tori, and sphere contributions. The second homology group, of course, is in a abelian group, and the homology classes, the second homology classes are represented by maps of oriented to simplices. So I guess this is if anyone who doesn't know a lot about it, this is probably lots to take on, but I guess a lot of this might be a bit weird to PI, but normal surfaces make it a lot more, I don't know, breathable. So the Thurston norm unit ball is a compact polyhedron formed in the space Z to D, where D is just the dimension, the rank of the second homology. And each point on this ball is a projection of relevant surfaces to H, to the second homology itself. So essentially we have, well, I have some nice slides up later. We have some manifold, and we're doing analysis on it by looking at embedded surfaces. For those embedded surfaces inside the manifold, they will have some of them, not all of them, some of them may contribute something to the second homology, because those surfaces might contain oriented two simplices, so oriented like subsurfaces, I guess. And these can be represented as some sort of points on the Thurston norm unit ball. And then all of the points, all of which represent the contributions to the second homology of all of these embedded surfaces, you take the convex hull of those points and you'll have some nice visualization in 1 dimension, 2 dimension, 3 dimension, whatever, that is your Thurston norm unit ball. Of course, where the dimension is the rank of the second homology. And so for a 3-manifold triangulation, the space of relevant embedded surfaces, we can define this homology map where NS is, just think of it as the space of surfaces. So we have a manifold, some sort of example manifold, list of we've enumerated all these embedded surfaces inside the manifold, and we denote NS as the space where those embedded surfaces are represented in. And, or at least the relevant embedded surfaces, so those surfaces that actually contribute to the second homology. And then we can define some homology map from that space to the second homology itself to obtain the points on the Thurston norm unit ball. I guess I will just really quickly say that most of this is pretty much built off of reiterating information from Stefan Tillman and Darrell Cooper's 2009 paper, The Thurston norm binormal surfaces, which was the original approach to this issue. And so we have this sort of, we have this visual representation of the Thurston norm unit ball, where each point represents a class in the second homology. And that class in the second homology is some surface, embedded surface inside the manifold. So of course we require the Euler characteristic to be less than 0. We're disregarding tori contributions and sphere contributions. So I guess as an example, we have the Whitehead link. And this is just the example of your Thurston norm unit ball. So this is just taken from Thurston's, 1986, sorry, not 1989. So the Thurston norm computationally, the main question that we're trying to tackle here is how do we construct the Thurston norm unit ball and hence a Thurston norm of any homology class in a computational sense. So to find a Thurston norm unit ball, we need to find all homology contributions of embedded surfaces in some triangulation satisfying that negative Euler characteristic. There's a couple of extra things that I'm not mentioning, like you have to make sure they're not vertex linking or thin edge boundaries and all this sort of stuff. So an algorithmic computation is a promising approach, as always, but an obvious problem arises is that how can we enumerate or even represent embedded surfaces inside a triangulation when their geometry can't be used as an input into a computer? So we have, let's say, we're embedding surfaces inside some manifold. How can we represent those surfaces in a computer and use them as a input into some sort of algorithm? So let's just say, for example, just take like a single tetrahedron. We have some sort of surface that looks like this. If we try and input that into a computer, we'll get something that looks a bit like that. A very upset computer being like, what are you trying to do to me? It's going to be quite mean to the computer. So this is where normal surfaces comes in handy. So they were first introduced by Helmuth Gneser. I don't know exactly how to pronounce it. I'm pretty sure it's a German name or a Baltic name or a German Baltic name. In 1929 to describe these embedded surfaces. And we say that an embedded surface can be isotoped to normal position. So we imply a discretized structure to embedded surfaces to isotope them into normal position, which just means we turn an embedded surface into a normal surface. So yeah, like I mentioned, normal surfaces discretizes the notion of embedded surfaces. And the way that we achieve this is that we essentially represent embedded surfaces as a union of discrete disks or normal disks. And I've called this a proto-lemma because it's not really a real lemma, but it's not really not a lemma either. Every interesting embedded surface in a three-manifold triangulation can be represented by an equivalent embedded normal surface. I won't go into it, but I've put interesting there because not every embedded surface can be necessarily isotoped to normal position. There are certain conditions, but by and large, everything we deal with in this sort of with the restrictions that we have in what my work's been on is pretty much every normal surface that I'm working with can be isotoped in normal position. So all of these conditions which are required for an embedded surface to be isotoped into normal position, I'm just going to say are interesting. So an example of a normal surface. Let's just say we have some very basic visualization of an embedded surface spanning 4 tetrahedra, 1, 2, 3, 4, and there's no particular interpretation of this. But if we were to isotope this into normal position, essentially turn this into normal surface, it may look something like this. So as you can see, we have this union of discrete normal disks, and we have this discretizing notion of this embedded surface. Without losing any topological information or making things too complicated. And so we would denote this whole embedded, this whole surface as the normal surface. And each of these discrete units is called a normal disk. We have 2 different types of normal disks. We call them triangular or quadrilateral normal disks. Essentially, a normal disk, they'll either be triangular or quadrilateral. The triangular normal disks will appear isolating the vertices of a single tetrahedron. So for reference, I guess a single normal disks will appear are bounded by the tetrahedron, so they appear only in one tetrahedron each. So triangular normal disks will be isolating each vertex of the tetrahedron, and while the quadrilateral normal disks will be cutting them in half, so dividing 2 vertices from each other. And for multiple tetrahedra, you can there's a thing that I won't go into called the matching equations, which describes how we can essentially glue these normal disks together to form a normal surface. So in this particular case, we have a quadrilateral glued onto a triangular. Here we have 2 triangulars glued together. It's just an example spanning 2 tetrahedra. So if I go back to this example, using these matching equations, which again I won't go into, we can sort of repeat this and build a normal surface out of it. And these normal surfaces will be the equivalent notion of the representation of our embedded surface. So there's a couple of constraints when it comes to building normal surfaces. One of the most important ones are called the quadrilateral constraints. Is that any normal surface that we're building or enumerating inside some triangulation of a 3-manifold, it must be a requirement that you never have 2 or more than 1 quadrilateral disk inside any single tetrahedron. So for example, if you have more than 1 quadrilateral inside a single tetrahedron, they will inevitably intersect, which is against the laws of life. So I guess a quick example of a normal surface spanning S1 cross S2. This, I guess, a bit more of a proper representation of what a normal surface might look like for a real manifold. One quick further note on normal surfaces is that we quite often deal with transversely oriented normal surfaces. So when we're dealing with a triangulated manifold with an applied orientation or an oriented manifold or orientable manifold, each embedded surface will have some equipped notion of an orientation on them, and thus when you isolate it to normal position, that has an equivalent notion in normal surfaces. And you'll have normal surfaces when you break them down into their constituent disks. Each of these disks will have some sort of orientation, either pointing one way or the other way, because they're just disks, so they only go 2 directions. For a triangular disk, you'll have either a long triangular disk, which is a triangular normal disk that pushes into a face, pushes into a two simplex of the tetrahedron, or you have a small triangular disk which will push up into the vertex that it isolates. For quadrilaterals, you only have two types. They'll always push into the two skeleton of the tetrahedron. So when we're looking at contributions to the second homology, the only orientation when applied to a normal disk that's going to contribute to the second homology will be these long triangles. So these triangular normal disks that have a transverse orientation pushing into the face of a tetrahedron. So when we're looking at these embedded surfaces or these embedded normal surfaces inside a triangulation, and when we're looking at these and we're trying to determine what the contribution to the second homology is, these, in my case, these disks are the only ones that I guess we're sort of interested in looking at. So when I said that not every embedded surface will have a contribution to the second homology, you can very easily imagine an embedded surface represented by normal surfaces that doesn't have any long triangular normal disks, as an example. So I guess I'll just obviously when we are looking at normal surfaces or transversely oriented normal surfaces, so normal surfaces with these orientations applied to it, we have 7 different types of normal surfaces. 1, 2, 3, 4 types of normal triangular normal disks, and 3 types of quadrilateral normal disks. So we have 7 types in total, with each direction of the transverse orientation that can be applied to each of them. We have 14 different types of normal surfaces when we consider transversely oriented normal surfaces. So as a result, all of these normal surfaces, embedded transversely oriented normal surfaces, can be represented as an integer vector in z to the 14n, where n is the number of tetrahedra. So this is where that number of considering the computational complexity that I mentioned earlier comes into play. So hence, now we've discretized the notion of embedded surfaces, and we've brought it to this form where we can use it as this linear vector integer in some computational algorithm, thus solve these difficult topological problems using linear algebra. So the key linear programming. The key result is that we can solve topological through manifold problems by methods of integer linear programming. Yay! That's opened a wealth of potential to solve very difficult problems with these methods. So far, as a couple of examples, it's been utilized in a wide variety of algorithms, analyzing topological properties in I-not recognition, 3-sphere recognition, the homeomorphism problem, et cetera. And now, of course, computing the Thurston norm unipole, and hence the Thurston norm of any homology class. So suppose, just to quickly hark back to the Thurston norm, we will recall that the Thurston norm itself is for any compact orientable through manifold M, the Thurston norm is a semi-norm or a norm defined on the second homology with coefficients in the reals, but can be easily extended to the rationals. It's a natural generalization of the knot genus, and the norm of any homology class is obtained by minimizing the Euler characteristic, which is a linear relationship to the genus and to the Thurston norm between its representative surfaces after discarding sphere and tori components. And of course, the Thurston norm unipole is the convex polyhedron with rational vertices that we can use to compute the Thurston norm itself for any homology class. So with this approach by normal surfaces, this is where the 2009, Stefan Tillman and Darrell Cooper outlined their first approach to Thurston norm via normal surfaces, and this is where we can pick up from. So if you want to create or sort of run or develop some sort of algorithm that will take as an input a triangulation of some Trojan triangulation of a 3 manifold and give you the Thurston norm unipole. So yeah, we want to try and take your triangulation T, find the basis of all normal surfaces satisfying a negative Euler characteristic, and then we want to find the contributions to the second homology of those normal surfaces and represent them as a point on the Thurston norm unipole. And then we'll have the Thurston norm unipole itself, and we can we can determine, compute the Thurston norm of any homology class. So I guess this work was more or less inspired by the desire to understand the topological significance of the faces of the Thurston norm unit ball. And the main result of Tillman and Cooper is that the Thurston norm unit ball for a closed, orientable, irreducible, and toroidal three manifold is a projection under a linear map of certain polyhedron, it's a projection under a linear map of a certain polyhedron in a transversely oriented normal surface space. And this polyhedron can be easily computed from a triangulation using linear algebra. In particular, the linearity of this projection comes from the fact that the Euler characteristic and the homology class of some embedded surface can be described as a linear function of the weights of that normal surface space. So that this convex polytope in the space of weights are defined by the linear equations given by the combinatorics of a triangulation. And the image under the homology map is the Thurston norm unit ball. I guess I'm putting weird, complicated terms. Dilemma, an integer vector representation of some ith embedded surface inside a triangulation, represented in the dimension z to the 14n, where n is the number of tetrahedral building of a triangulation, will have an integer vector representation of its second homology class, if it contributes to the second homology. I guess just to give a couple of really quick, this isn't super important, but this is sort of how the generalization of the Euler characteristic and the homology map as linear functions. So essentially there is some linear map from the space of oriented normal surfaces of some triangulation to the reals, which agrees with the Euler characteristic. And then there is some surjective homomorphism mapping from the space of transversely oriented normal surfaces to the second homology class, which agrees with the homology class for some surface S inside your triangulation. So again, this isn't, it's important, but I guess it's not super important for me to mention, but it's just, this is where we get the second homology contributions from. We're interested in looking at an algorithm that would take in some triangulation of a three manifold. We want to enumerate a certain class of normal surfaces. So recall that we want normal surfaces to satisfy negative Euler characteristic. Can be vertex linking, can be thin edge boundary, whatever. None of that's really the Euler characteristic is the most important one. And thus we can we can determine their contribution to the Thurston norm. So the algorithm will take in this triangulation and will output the points of the Thurston norm unit ball. And taking the convex hull of these points will give you your the Thurston norm unit ball itself. And once we have the Thurston norm unit ball, you can determine compute the Thurston norm for any homology class for whatever your input was. So this is one of the results of my thesis, was actually implementing this computationally. I must apologize, first of all, because there's no matter what examples I sort of ran through the algorithm, there's none of them really gave like a nice visually aesthetic result. So pretty much most of the things that actually gave good result, or interesting data or interesting results, were things with a second homology rank of 1. So it was only a one-dimensional, like just an integer line. The Thurston norm unit ball is just represented on the integer line, which is visually annoying, but I guess topologically exciting. So I don't know, maybe I should, before I do that, maybe I should very quickly just share my screen. So this is essentially how one way I get my data. So can everyone see the Regina? Awesome. Yeah, so of course I just, Ben Burton is my supervisor, so of course I use Regina, and also who the hell wouldn't if you're doing anything like in low-dimensional topology of normal surfaces. For anyone who doesn't know, Regina is an amazing thing. And if you're doing anything, normal surfaces or 2, 3, 4 dimensional topology, it's your go-to program for things. So essentially, I'm just in this short script, I'm just looking at, I'm taking like a big census of all of these closed and orientable manifolds. And I'm just looking at are there any anything with a rank, anything with a homology rank greater than or equal to 2? And I'll run this, and here we have a bunch of manifolds that satisfy these conditions. And this here, these big letters at the end, will give an isomorphic signature, which is basically just a unique signature you can use to draw the information of that manifold. So I know theoretically, if we were to run this through the algorithm, which I'm not a computer scientist and I'm not very big on codes. So if this looks messy to you, there is a method and it's unique just to me. So I've run this through the script, and this could not compute the Thurston norm. So that's wouldn't work. I'll try it one more and see if something happens. Huzzah. Okay, so we got something. So for this surface, the second one here, SFS T12, whatever, I don't really know topological what this means. I think it's some sort of Seifert surface, however it's pronounced, with some, I don't know, I think this describes some sort of den filling, I'm not exactly sure. But in any case, we run it through the algorithm, and we check that it has a non-trivial second homology, which is true, and we'll get, we've got 2 points on the Thurston norm uniball. So just on the vertical integer line. So yeah, that's our Thurston norm uniball, just 2 points, which is pretty cool. So that's sort of how it would run. And what I did to test my algorithm was essentially run lots of different conditions through the script and draw a lot of different data and just running every single one of them through the algorithm to look at the results. And this is where sometimes I had to wait. I think I waited at most a bit under 2 weeks for the 14 tetrahedral triangulation, which is good fun. Anyway, so so going back to this quick other example on the slides before I finish up. So we've taken this example manifold, this example triangulation on a manifold. So you can take zero efficient triangulations or simplicial triangulations, it doesn't really matter. Just recall that we're not, this algorithm doesn't work for cusp manifolds. So looking at more hyperbolic structures or actually I'll mention that later, who cares. The basic information of this triangulation is that there's 13 tetrahedra. The second homology is non-trivial and the rank is equal to 1. So we expect to get a Thurston norm uniball represented in along the integer line. So we run it through the algorithm and we enumerate a basis of normal surfaces embedded in that triangulation such that the Euler characteristic of the surfaces are negative. And we obtain 430 normal surfaces. So recall that each of those surfaces are represented in as an integer in the dimension z to the 14n, in the dimension 14n. So for the 13 tetrahedra that we have building up this triangulation, each of those 430 normal surfaces is some integer of the 182nd dimension. So we can sort of see why the Thurston norm and other notions in topological and algorithmic complexity is important in keeping things nice. So of these surfaces, we want to check which ones have some long triangle. So which ones have components that contribute to the second homology, and thus which surfaces contribute to the second homology. Of these, this is all running through the algorithm, we obtain 86 normal surfaces. So we get 86 normal surfaces in the represented in a space of the dimension z to the 1, because the rank of the second homology is 1. And our output finally, it will kick out, will spit out a result. It's these 86 vectors. They're not necessarily unique. They're either -2, -1, 1, or 2. So visually, we get this very aesthetically annoying Thurston norm uniball looking like this. And once we obtained a Thurston norm uniball, it's a pretty straightforward process to calculate the Thurston norm of any homology class. So any of these integers along the line will represent a homology class, which would be some, which could be representing some surface, in some embedded surface, and we can calculate the Thurston norm of any of these homology classes. But yeah, that's the result of the algorithm. So I guess looking at what it actually spits out, you see this is an important, the only important thing is these last numbers at the end of the line. So we get -2, -2, -1, 2, and 1. And each line represents one of those 413 normal surfaces. So of course, the rank of the second homology is 1, so we get these points on the integer line. If the rank was equal to 2, we would get a Cartesian plane representation of the Thurston immutable. If it was 3, we'd get a really nice convex symmetric polytope, which would be really, really cool to look at, but not in this case. So I guess just to summarize, to revisit the main problem, the algorithmic complexity increases exponentially from the number of tetrahedra inside of the 3-manifold triangulation, as well as the base of the exponential. The Thurston norm is a very important notion as a measure of topological complexity, and keeping the base of the exponential at a small level, you'll obtain some results that's a rough generalization of the knot genus, and will give you like the minimum Euler characteristic of embedded surfaces inside whatever manifold you're doing stuff on. Normal surfaces are very, very important, a very useful way to discretize these notions of embedded surfaces, and allowing us to open up our range of tools into computer linear programming and linear algebra. Of course, as part of my honors thesis, I developed just a computational implementation of this algorithm, which was originally outlined by Stefan and Daryl, where you input a 3-manifold triangulation, you output the Thurston norm uniball, and hence with the Thurston norm uniball, you can determine the Thurston norm of any homology class, which will give you the minimum value of complexity of a surface representing that class, of an embedded surface representing that class. So I guess a couple of very quick further considerations. You can reducing computational complexity, looking at different constraints on normal surfaces. I haven't done a lot of work into it yet, but you could constrict the contributions of the normal disks that make up your normal surface to just small triangular disks, so just the triangular disks with an orientation pushing into a vertex, to just quadrilateral disks, or of course, as we've done, is just the long triangular disks pushing into the 2-simplex, into the face of the tetrahedron. So yeah, looking at different classes of normal surfaces, any programming shortcuts that I'm just not too much of a peasant to know. Exploring the bounds on the Thurston norm, so this is where like Alexander invariants come quite handy. Looking at like the lower bounds of the Thurston norm. And of course, any further algorithms based off of Thurston's ideas or proposed by Stefan and Daryl. So, for example, determining the fiber faces of the Thurston immutable, which are quite handy. I guess I'll mention as well, just really quickly, 6 days ago now, William Warden, along with Stefan and Daryl, I think William Warden's from some university in Texas. Pretty cool guy. He basically did the same, but a lot more. For a lot longer and a lot more, and he's essentially developed an algorithm that will compute the Thurston norm immutable of cusped manifolds. So a much larger class of manifolds and a lot more detail. And that paper was just released 5 days ago, 6 days ago, which is pretty exciting. So yeah, what I've just talked about today is just a very, very small subset of what he's done now. So yes, very new and dynamic field, and there's a lot of cool stuff going on, which is why I think looking at notions in topological complexity in computational topology is a very exciting field to read about and do stuff in these days, because there's a lot of things going on. But anyway, yeah, that was everything I want us to ramble about. Thank you.
Awesome. All right. Let's all thank David again for a great talk.